Hello everyone. So today we will be discussing the topic water hammer in module 3 of the course ME 200, that is fluid mechanics and machinery. So module 3 contains two main topics. One is water hammer and the other one is flow through siphon or a siphon effect. So in this section we will be looking at both of those topics. First we will look at what is water hammer. So water hammer is also known as hydraulic shock or fluid hammer, etc. So from the name itself, you can uh, you can visualize it as a hammering sound created by the fluid. Hence the name, it is called fluid hammer or water hammer. Now the question is how this hammering sound comes. So that is explained in the second point. It is basically a pressure surge or wave caused when the fluid, usually a liquid, but sometimes also it can be gas in motion, is forced to stop or change the direction suddenly. So what is happening here is that when a liquid is flowing freely through a pipeline and suddenly we are changing or stopping the direction of the flow by some mechanism, for example it can be a valve or it can be bent in the pipe, etc. So the smooth flow of the liquid or the water is obstructed here, and therefore we can tell that there is a sudden momentum change happening. This sudden momentum change, what it creates is a pressure wave. So this commonly occurs when a valve closes suddenly at the end of a pipeline and a pressure wave propagates in the pipe. This pressure wave uh, is so can be so intense that it can create noise and vibration, and ultimately it can lead to collapse of the pipe. So this vibrating sound or a ringing sound or a hammering sound is commonly referred to as water hammer. So it is a harmful effect or a bad effect. And what are the remedies to avoid this? That is, one is by fitting accumulators or providing expansion tanks or surge tanks, blow off valves, etc. So the idea here in all these cases is to reduce that effect of intensity of the change or the stoppage. So for example, in the case of expansion tank, if you are providing an expansion tank, that flow of the liquid will be obstructed or will be changed only gradually, rather than a sudden momentum change or a sudden intensity increase. The expansion tank or surge tank, etc., will slow down the effect and in a such a way that the intensity is reduced and that hammering sound can be avoided, and hence the pipe life can be extended. So in this figure you can see an arrangement where there is a tank, and the tank is having a level up to H, and there is an outlet pipeline. Say it is having a length of L and it is having a diameter of D, and hence the area is A, and the water is flowing through this pipeline with velocity V, and there is a valve B which is at the other end of the pipeline. So as I said earlier, when the water is flowing freely through the through this pipeline and this valve B is suddenly closed, there will be a pressure wave will be propagating through this pipeline, and it will be going and hitting this valve. So if we clearly observe, there will be a ringing sound or a hammering sound, and this is known as water hammer. And the factors which are affecting the water hammer, or the factors the water hammer depends upon, are: one is the velocity of the water in the pipeline, which is here shown by V, and the length of the pipeline, okay, and the time taken to close the valve, whether we are gradually closing the valve or we are closing it very quickly, And last one is elastic properties of the material of the pipe. That is what material it is made up of, whether it is a stainless steel pipe or a PVC pipe. Those kind of things also depend, also affect the water hammer. Now we come to the second topic, that is siphon effect. So what is siphon? So to understand siphon, consider two tanks which are separated by a distance, and in between these tanks there is some obstruction, maybe a hill or a ridge, etc. So siphon is a pipe connecting these two tanks, or it can be it is a bent pipe connecting these two tanks, through which the liquid is transferred from a tank which is at a higher level, say A here, to a tank which is at a lower level B. The problem is that these two tanks are far away, and there is some obstruction in between them. It can be a hill or a high level ground as shown below. So in this figure, A is the tank which is at higher level and B is the tank which is at the lower level, and this is the siphon tube or the siphon pipe, and the highest point in this pipe is known as summit, the summit point. Okay, now the point C is called the summit or the highest point on the siphon. So the pressure at C will be less than that of the atmospheric pressure. Now the pressure at sea may be reduced to minus 10.3 of water, that is theoretical value, but in actual practice it is shown that it is only minus 7.6 meters of water, and the difference between these two is the 2.7 meters of water absolute. Now the significance of this value 2.7 meters of water absolute is that whenever the pressure at that summit point or the point C becomes less than that of the 2.7 meters of water absolute, the flow will be obstructed, or in other words, the flow will not take place, or we cannot transfer the liquid between the two tanks. Why? Because the dissolved air and gases would come out of the water and collect at the summit, and this would cause blockage of the pipeline, and hence the flow of water will be obstructed. Now, siphon is used in the following cases, that is, we have already discussed. One is to carry the water from one reservoir to another, which is separated by hill or ridge, or take out liquid from a tank which is not having any outlet, and to empty a channel which is not provided with any outlet sluice. Now we will solve a problem involving this siphon tube. A siphon of diameter 200 mm connects two reservoirs having a difference in elevation of 20 meter. The length of the siphon is 500 meter and the summit is 3 meter above the water level in the upper reservoir. The length of the pipe from the upper reservoir to the summit is 100 meter. Determine the discharge through the siphon and also the pressure at the summit. Neglect minor losses. The coefficient of friction F is equal to 0.005. Let us write the given things. That is, first one is diameter of the siphon, which is given 200 mm, that is 0.2 meter, and difference in level of the two reservoirs. That is, just have a look at this figure. A is at a higher level and B is at a lower level. So difference in levels, this is shown in this figure as 20 meter. So we'll represent it by capital H is equal to 20 meter. And length of the siphon, that is length of the siphon tube throughout the entire length from reservoir A to B is capital L is equal to 500 meter. And height of the summit from the upper reservoir. We all know that summit is the point C and height from the upper reservoir is A. So this height is 3 meter. That is small h. Length of the siphon up to the summit. So length of the siphon up to summit is 100 meter as shown in this figure. L1 is equal to 100 meter and the coefficient of friction F is equal to 0.005. How to solve this problem? So in this problem, first part, we are asked to find out the discharge. Okay. Now, as in all Bernoulli's equation problems, we are applying Bernoulli's equation between point A and B. that is between the two reservoirs. First of all, between the two reservoirs, that is reservoir A and reservoir B. So here minor losses are to be neglected. So the only loss that is happening when the flow take place between A and B is due to friction. So applying Bernoulli's equation between A and B, we can write PA by rho G plus VA square by 2G plus ZA is equal to PB by rho G plus VB square by 2G plus ZB plus the losses that is happening between A and B, which is the frictional losses. Now here PA and PB are the pressures at A and B, which are the tanks. So the tank is exposed to the atmosphere, so the pressures happening there is atmospheric pressure. So we all know that the atmospheric pressure in our problems etc and all, we take atmospheric pressure as the datum of the reference. So this can be regarded as 0. So we'll write PA is equal to 0 and PB is also 0. Now next is VA and VB, which is the velocity of the water or the fluid at A and B, which is at the tank. So inside the tank we are assuming static conditions, that is there is no flow or there is no velocity. So VA and VB will be equal to 0. So substituting all those values, 0 plus 0 is equal to ZA is equal to 0 plus 0 plus ZA is equal to 0 plus 0 plus ZB plus HF. Or rather we will write ZA minus ZB is equal to HF, which is equal to 4FLV square by 2GD. From Darcy's baseback equation, we can know that head loss due to friction is 4FLV square by 2GD. Now the differential level between A and B is already given in the problem. ZA minus ZB is 20 meter. So substituting that value, 20 is equal to 4 into F is 0.005. Length of the pipe is 500. Velocity we don't know. So V square by diameter of the pipe is 0.2 meters. 2 into acceleration due to gravity 9.81. So we'll get V is equal to root of 20 by 2.548, which is equal to 2.80 meter per second. So once we got the velocity, we can easily find out the discharge. So from continuity equation, we know that discharge is equal to Q is equal to AV. So V is 2.80 into area. It is a circular pipe, so the area will be pi by 4 d square. So the discharge is 0.0879 meter cube per second, or converting it into liters per second, we get the answer as 87.9 liters per second. Now the first part of the problem is already solved. Now second part, we are asked to find out the pressure at the point C. So to find out the pressure at the C, we have to apply Bernoulli's equation, but this time between the points A and C, that is between the upper reservoir and the summit point C. So we will write the equation PA by rho G plus VA square by 2G plus ZA is equal to PC by rho G plus VC square by 2G plus ZC plus the loss happening between A and C, which is the head loss due to friction. So here again PA is the atmospheric pressure, VA is 0 due to static condition, and ZA is also 0. Why? Because we are taking the datum line here as passing through A. So A will be 0, and from that 0 datum line, C is at a higher elevation. So ZA will be 0, but ZC will be 3 meters. And we don't know PC and V, etc. Okay, so substituting these values, 0, LHS, all things will be 0. So 0 is equal to PC by rho G. We have to find out this value, PC by rho G. And V, we just have obtained the value of V, that is 2.8. So 2.8 square by 2 into 9.81 plus 3. Again HF1, we already have used HF in the first part, so we will use HF1 here. So again by Darcy's baseback equation, 4FLV square by 2GD. So 4 into F is 0.005, L is 100 meters. The 100 meters is the length of the pipe between A to C, which is given in the problem. So L is 100 meters, and V is 2.8, so V square is 2.8 the whole square into 2 GD, 2 into 9.81 into D is 0.2. So we will get the answer PC by rho G is equal to minus 7.399 meters of water. This is the pressure at the point C or the pressure at the summit. So hope you have understood how to solve the problem in the siphon flow through siphon part, and hope you also have understood the topic water hammer and the siphon effect. Have any doubt, please feel free to contact me. Thank you so much.